Hey, welcome back. Good to see you again. What have I got for you here? Have a look. These are all functions like what we were doing before, but this time we're talking about composition of functions. If you're a composer with music, you can make a lot of nice sounds. And if you're a composer in maths, you can make a lot of interesting functions. So here we go. We're going to construct or compose functions which consist of more than one part or more than one function. So what I'd like you to do now is just have a look at the functions I've got there for you and the way they're written. Can you see that there are two distinct types? Let's have a look. This one here is written as f of x equals, and this one, g of x equals, and p of x equals. Now that's one type. And can you see the others are written slightly differently from that? And they are, of course, this one here, this one here, and this one here are all using more the mapping notation. X maps on to that value there. So just trying to do a little bit of revision there. Is there anything else that looks slightly different between these functions? Have a look and see what you think. Can you see it? Well, this is probably the simplest function, just one operation done to the variable x. This one up here is a bit more complicated. There have been two things happening. 4's been added to x, and then we've found the square root of it. That looks like a composite function. And here, the most complicated composite function or composition of functions would be this one here. We've actually squared x, we've then subtracted 4, and we've taken the cube root of the whole thing. So that's a composition of actually, probably you'd say there three functions. So that's what we're talking about. How in mathematics we will want to compose reasonably complicated functions in practical situations. So let's go down and have a look now at this one. And I just want to mention here from Pearson's, again we're working with Pearson's textbook, this little icon refers to a program that you can have on board, an autograph program. It's a bit of software, a very clever piece of software, and now enables you to do graphing and to look at the interactions of various functions. So I'd encourage you to have a look at the textbook and click onto that and see if that gives you a better visual understanding of what's going on. Now for this composite function, we're going to choose the one I mentioned before, this little dude here. Why is it a composite function? Well, I suppose with Pearson's here, you have to actually perform two computations to work out the value of the function when x is 5. First of all, you've got to put 5 in the position of x in the function and add 4, you get the answer 9, and then you've got to find the square root of that. So that's the first step, and then you find the square root of 9, which is 3. So there are actually two distinct steps in finding the value of f of 5, because f, that function f of x, is said to be a composite function composed of two parts. That's the idea we're working on in this little presentation here, and let's have a look at our notation or terminology used here. So we could think of f of x as one function done on another. So what was root of x plus 4? Well, really we could have said that if we did h of x, let's do h on x and produce the expression x plus 4, then we'll do g on the result of that. So you're applying one function to the result of the other. It's sometimes called, over here, Pearson's used it here, a function of a function. So you apply the function to the variable x, get an answer, get a range value if you like, and then put that in place of x in a second function. So you're composing a g of h of x, sometimes written as function of a function. So it's a way of explaining how we can build bigger and more complicated functions. Let's have a look at some more notation. The IB like this notation here. So instead of g of h of x, which says, you know, find the value of the function h done on x and then use that within g. So instead of just g of x, g is going to operate on, in here, the result of h of x. So I've got to do one and then put it in place of the variable in the other. Sometimes this is called the argument of the function, the value which the function is going to operate on. Can you see, therefore, that GOH is like this? It's saying G is going to operates on the result or the range value of H. GOH. G operates on the result of H. Got to do H first. So therefore, when you choose to operate H, you've got to choose a value that is in the domain of H. Then you get an answer, which is the range of H, the result coming out of the function H of x. And that's got to be within the domain of G. So we're getting a little bit of a flow on here. The result of one, the range of one, must lie in the domain of the other if you're going to have a final answer for your G operated on H function, which is equivalent to G done on H of x. So please just pause now and think what this notation means. Two different statements but meaning the same thing. Here GOH or G of H of x means G must operate on the result of H. You do H first and then stick it in the variable hole in G, or the argument for G. So we're getting some ramifications down here of what functions will work and what won't work. Because once you've done a function on the variable, you have a range value that must belong within the domain of the next function, so it can then operate on it. We're going to do some practice on that in a minute. So here's the definition of the composition of two functions, and of course we've just written it up above there, that G of H, and in X's sometimes this X is left out. GOH means G operating on the result of H. Can be also thought as G done on H of X. G of H of X, if you like, equals G of H of X. So, or just GOH in bracket X. Okay, so what would be the domain of G operated on H, or G of H of x? So the domain is any x that you can do H to, because the first thing you're doing here is computing a value of H of x. So the domain of the whole G of H of x function is a domain of H. It's got to work in H first, and then you produce a value and G can operate on that. And then you can only have that possible domain value if it's within the domain of G. G must be able to work on it then to produce the range of the overall function. And I guess you can see then the range is equal to the range of G. Okay, depending on any restrictions of on the domain. look out for domain restrictions there. You might not produce the full range that G normally does, because H is not producing the full domain of G. So we're going to play around with this rather like a puzzle here for the minute. So this time, instead of showing you the answers straight away, I'm going to get you to see what you can work out here. What is F operated on G of 5? Well, can you see you'll need to work out G of 5 first, get an answer, then put it in F. So you might like to try to do that. G of 5 would mean replacing x equal to 5 in here, get an answer, and then that answer F is going to operate on. And F is going to multiply it by 3. Right, have a go at that. What we'll do is we'll go down and have a look at the answers to those. The first one. So here we've done it. G of 5. So putting 5 in there into the function, take away 6, you've got the answer 4. F of 4 is 3 times 4 is 12. So what about the second part, the more general part, finding an expression as a single function for that composite function? So what it means is we've got to operate F on the result of G, which is 2x takes 6. G is 2x takes 6. So now we operate F on that result of G, and what does F do? It multiplies the variable by 3, so we need to do that on the result of G. So we're going to have 6x take 18 as our result. All right, you might like to pause the presentation and have a go at these other parts, some with numbers over here in them, and then writing general expressions. Anyway, coming down to show you the answers there, and you can come down and look at those when you've had a go. Notice it's probably preferable to try to work down the page. In Pearson's textbook here they've worked across the page to save room in the answers, but overall it's better if you can work down the page, a bit more clearly stated. Alright, let's move on then and look at another example that we could do. This is finding expressions now, not evaluating them, but saying we want F to operate on G. So G is going to be done first, because F is waiting to operate on G's answer. You could actually think of it in the operator model as a G of X provides an answer and you feed it in to the operator F of X, and out of the function comes F of G of X, or that idea there, similar notation. So if you think of F operated on G in that order, you actually do have to have a G answer so that F can operate on it afterwards. Okay, and similarly here we're doing it in a different order. This would have to be done first. Done first there. Why? Because G is going to operate on the answer of F. So if you want to think of it in an operator form, the F of X has to feed in because G wants to operate on it. And then it'll come out to be G of F of X, or G operated on F of X, either of those two notations. So you might try to combine those. remembering that G does this to the variable, then you take that and feed it into F. And what will F do? It triples the value of X and then takes 6 away. All right, have a go at those two. Might pause the presentation now and see what you make of those. Well, going down to the answers then, what's happened? Well, here we are. G was done first, so we end up with a third x plus 2, which we stick that in the f function. Here's the f function. This is f of a third x plus 2, because f of x was 3x, so now it's 3 times the result of g minus 6. And so we end up with the function just x. So can you see what's happening? If you apply f of x first, you'll get that answer, and then you have to stick it in g. What does g do? G finds a third of x and adds 2. So you are replacing the argument or the variable in that second function with the result of the first function. It's a substitution into the bracket of that second function, if you like. Here they've turned out to be the same, which is very, very unusual. When you do f operated on g, you don't usually get the same answer as g operated on f. But this is a special case, and Pearson's making that comment there. You might like to pause the presentation and read that, and we're going to look at that special case later on. Okay, are you getting the hang of it? Let's come down. Decomposing composite functions. Did you leave your function out of the fridge and it's decomposing? I don't think so. Small joke. Decomposing composite functions means breaking them down, breaking the composition down, reversing the composition, and trying to actually see what the two parts are. So here let's go back to this one. To get that function, what are the two parts? Well, there's the square root of x plus 4. Now the x plus 4 was done first, so we could call that, let's call h of x equal to x plus 4, and then if we did g to it, g would be that, g of x would be the square root function. So if we had g operated on h of x, that would be the square root of the result of h done first. Can you see that? You can actually start to break or decompose the composite function down. This is sometimes useful in calculus later on to see what functions are going on. You can read what Pearson's have got there about looking at those two functions. You're really wanting to work out which one was done first, and then that becomes the function that the second one has to operate on. You can think of it like this or like that. It's clear in this notation that g is going to operate on the result of f. So f is done first in this scenario. Right, you might like to pause the presentation, perhaps read some of the work there and think about it. Let's move on then to another example. Example 9. Each of the following functions is a composite function. For each, find the two component functions f and g. Well, can we do what I've just done there? Said each one, so this, we've written this as a mapping now. So this function h, did it consist of two things? A g done first and then an f done? Because that's what they want us to do here. They want us to construct an h of x which consists of g done on x and then f done on g. You might like to pause the presentation and say, can you find 2 bits there? And similarly here, are there 2 things, 2 operations, 2 functions that have been applied to get our function k? Our function k is a mapping of x onto 2 to the 4x plus 1. And what about over here? We've gone back to the p of x equals notation, not the mapping notation. The IB would like you to be very flexible with the 2 forms of notation. H of x, it doesn't matter what letter you use there, such that x maps onto something, or simply h of x equals. Are 2 different notations, one involving a mapping and one just involving an equating. You might like to pause the presentation now and have a go at these 3. Which one was done first, and then what happened to it? Well, in this case, we'll have a look at the Pearson solutions down the bottom, but I'll go a bit more slowly through here. Now, this h function, h of x equals, now can we see f operated on g, and I'll just do that again here, f operated on g of x, can we actually put it in that form here? Well, if we write it in this form, it means there was a function g done first. Well, what was done first up here? Well, we did a 1 over, but first of all, we had to do x plus 3. So we're going to say g of x equals x plus 3. And then f of x was 1 over x plus 3, or the function 1 on x. Can you see that? Identifying what was done first. So if you do this first and then apply f to it, you will have 1 over x plus 3 at the end. Let's have a look at this one here. Are there 2 functions? Well, I think you can see that 2 was raised to the 4x plus 1. So the first thing you had to do was to find 4x plus 1 value and then stick it in place of x in the function f of x equals 2 to the x. Let's just check that one. F operated on g of x would mean that f has to operate on g, so instead of 2 to the x, it'll be 2 to the 4x plus 1. A few different ways of thinking about that. Okay, let's have a look at this one here. What are the 2 functions here? Well, I think you can see we're doing the cube root, but before we do that, we have done g, which is x squared take 4. And then we've done f of that, f on that, which is the cube root function, cube root of x. So if we wanted to do f operated on g of x, we would stick the g in place of x in the f function. And we would have, instead of the cube root of x, we would have the cube root of x squared take 4. So we're trying to look at the structure and what makes up more complicated functions. Okay, let's move down. We'll have a look. Here are the solutions from Pearson's there. That's good. So you might pause that and just check the answers there and make sure you can see how all of that works. All right, so moving on then, we're going to look at domain and range because we've built up a composite function, a more complicated function involving at least 2 parts, And so we need to say, well, how would you trace through the domain and range then? So we've done this before, G operated on H. So what's got to work? Well, first of all, you do H is done first, because this says G is going to operate on it. So you can't operate on something you haven't got an answer for yet. So you've got to find H of X. So what's the domain of the overall composite function? It must be the same as the domain of H. Okay, and then what's going to happen? You will produce range values out of H, and they must become the domain of G. So here then you'll produce H values which will work in G, which are in the allowable domain of G. And then your possible range of a function at the end, the range of the composite function, will be the range of G, if we can achieve all the values attainable usually by G. So here they've gone into a little bit of an explanation there. X must be in the domain of H, and H of X must be in the domain of G. And so if you were going back the other way, this is an important point here, that it is not usually the case that if you do H operated on G, the domain would be different generally. Because here what you're looking for is to do G of X first. And if you do G of X first, then you require that the domain be the domain of G, because you're doing that first. So the domain of a composite function is the domain values of the function done first. So here it's G of X. All right, so you might like to pause and just think about some of that, maybe rewind it and read the stuff again and see what you think. Well, here's another example. And we're nearly at the end. Please note that we've got the autograph icon there, so we're not going to go into that in this presentation, but you can do that yourself using the textbook, the e-version of the textbook. Okay, so here we have two functions. G of X is X squared take 4 and H of X is root X. Find G of H of X and its domain and range. Okay, G of H of X. So that means G has to operate on H, which would be G done on root X. Okay, because H is done first and G is operated on it. So if we do G on it, what's G do? G squares it and takes 4. So let's square root X. That would be X. And take 4. So our actual composite function, G of H of X, is that one. Now what would its domain be? Well, domain is the domain of the function done first. So that's the square root function. So the domain equals what? The set of X such that X is greater than or equal to 0, isn't it? Because you can only find the square root of 0 or a positive number. So that would be the domain of the composite function, and the range of the composite function is going to be the range of this function G at the end. And we're going to say, well, here X is a member of R, but with the square root of that one there being restricted to positive values, here we're going to say the range is equal to the set of Y. Now we're only going to be putting in positive values, so here Y such that Y is going to be what? If we're only putting 0 or positive values in here, Y is going to have the smallest value of neg 4. It's going to be greater than or equal to neg 4. Okay, so let's go down and look at Pearson's use of notation down here with these. And they've set it out down the page this time, so I think you can read that through pretty nicely there. Just saying at the end, this is a tricky bit. If you're only allowed to use values of x greater than or equal to 0 because of the domain restriction on root x, then that's going to affect the range allowable. It won't be the full range of x take 4 because we're only allowed to start at positive values because we've got to get through that square root function. All right, well, you might try the second one here and see what you think. And then, so pause it now and see if you can play around with that one and come down then and mark it down here so you can see what they're doing. All right, I'd like you to study that and make sure, because we're putting a few things together now. It's important with maths learning being sequential and cumulative, that you keep accumulating the knowledge as you go through the sequence of concepts there. All right, so we'll come down to the end, which is this set of problems here, exercise 2.2 from Pearson's, and so I'll just bring those up. There are the problems there that you might like to, hang on, we'll just get this in a better position there perhaps. So here it's asking you to work with the operation between two functions. Always remember that the notation f operated on g means you've got to have g done first so that you can stick it into the result, the range of g, stick it into the f function and do the f work on it. A number of students over the years seem to get this in the wrong order. I don't know why, because we need to think of this as implies f operates on g. So you can't actually start any work with f until you've found the result of g, because f is going to operate on g. And if you like, you're going to have a result of g going in there to work f on it, and then you'll get the range of the composite function f of g of x coming out the other side, if you like. But you actually have to start with a feed-in value, a domain value from g. G has to be done first. All right, I think all of these are okay because they are all examples similar to what have been given going through the presentation there. So what I'd like you to do is to maybe have a go at question 1 and 2 and then mark it and so on. So I'd like you to pause the presentation and try that. What I'll do is take you down to the answers so that later you can pause and mark for yourself. So here we've got question 1 done 2 ways. Pearson's here have got a paper 1 type answer, paper 2. Please remember why, because paper 1 there is no access to any calculating device at all. No GDC, no graphics calculator. So you need to be able to do it as we've been doing it earlier. I've replaced Pearson's graphics display calculator solutions with a Casio set here, where you would actually, if you're allowed to use a calculator, you could actually work out g of 5, I think here, g is 1 over x take 3. So you could enter it into the calculator, draw the graph, and then if you go to shift F5, then you can actually find a calculation of y by going to the other page and doing a y calc for a particular x value. So up here, if you wanted to find g of 5, then you could draw the graph of g, which is 1 on x take 3, and go to gsolve and do a y-calc for an x of 5. It probably isn't worth it for this level of problem here, because they're not too bad, these questions. All right, so you can come down and mark that later on. Let's just bring up the rest of them. Let's go to question 5 perhaps. So when you get to that, you can pause it and mark your work for those few questions. I'll just display the others in pieces here. So if we went through to question 6 to 10, just marking those off, come down there when you've had a go, and then I think we can fit on 10 through to 18, just there. Yeah, 10 through to 18. So when you've had a go at those also, come down, pause the presentation and see what is going on there. Now all of these problems do have match-ups with the examples that we've gone through within the presentation. So your job now is to have a go at those questions and check your answers as you go. Don't do too many problems, get them all wrong and find that, oh, everything I did was wrong. You should check along the way. Right, well, hopefully you're getting pretty confident now. Things are building up and we're able to work with more and more complicated functions. So I look forward to seeing you in the next presentation, but for now, it's cheers from me.